This is EE 619, lecture 21. So I had left you with a question in the previous class. We considered two dynamic circuit configurations. This was case 1 and this was case 2. So all of us agreed that both of them are implementing the same function. And if I were to estimate the output capacitance here as C1 and the capacitance here as C2, we would expect our C2 to be much smaller than C1. Therefore, delay-wise, this circuit seemed to offer some benefit. But I mentioned that this circuit is not used. Did anyone figure out the reason? VDD by 2 to? So what do you mean by VDD might go to VOH? VDD is here. Huh. Okay. Output is floating. Why would it reduce? So the leakage could be present here also, right? You're in the right direction, but leakage is present in both the circuit. If there is leakage, it would be present in both the circuits. But that thought process is in the right direction. So any other suggestions or any other ideas on this? Which one? Oh, sorry, this is also NMOS. So let me give you a scenario. Let's assume, so let me consider the capacitance at this node, right? It is some Cx. Let's assume that initially PDN was on, due to which Cx was completely discharged, right? And then the evaluate phase begins. And let's assume that in the evaluate phase, PDN is off, okay? So PDN is off, but because you are in the evaluate phase, this transistor is on, okay? Now, since PDN is off, you would ideally expect C2 to be floating, wherein Y remains at VDD because of the charge stored during the pre-charge phase. So now you see that this transistor is on, which means now the C2 and Cx capacitors are shorted. And if Cx is originally discharged and C2 is at VDD, when you short them, there will be charge sharing between C2 and Cx. Because of which this VDD will now reduce. The output is now going to come down from VDD. The exact value to which it will settle will depend upon the values of both C2 and Cx, right? So now in the evaluate phase, your capacitance C2 is floating. Ideally, it should have been at VDD, but now it is at a value lesser than VDD. There is no means to pull it back up to VDD because in the evaluate phase, the pull-up network is off, right? And a value lesser than VDD, now depending on how low it has gone, it might enter into the indeterminate region, or even if it is still considered as a logic one, you are unnecessarily risking it becoming indeterminate in the presence of noise, right? And since this is now a matter of functionality, your circuit could give incorrect values. We never prefer this circuit. We'll always stick with this. Now, in this case, once the PDN is off, your output capacitance is disconnected, right? There is no other capacitor that is connected to the output capacitance. So charge sharing is not a problem in case. Is this clear? Any questions? Okay. So now let us look at some timing information in combinational logic circuit. So let's consider a sample circuit. Let's say it has inputs I0, I1, I2, and I3. This is D0. And this is D1. So effectively, you have some combinational logic with input as I, which has 4 bits, and output as D, which has 2 bits. So if I were to look at its timing diagram, so let's say the input is I, it's changing at some instant as shown here. How would the timing diagram for I look like? So it will start changing sometime after this point with a small delay, right? Will it settle to the right value in one go? Between D0 and D1, which bit is likely to change first? D1, right? So you'll get some change in D1. Then after a small time delay, D0 will also settle. So your output is going to transition multiple times before it reaches the final value. So both these transitions are a result of the transition at this input. So we mark it with an arrow like this. What should we call this delay from the input to the first point at which the output starts to change? So there are 2 delays now. The first time instant at which the output is beginning to change, and the time instant at which the output has finally reached the settled value, stable value. The 2 delays that we know of are contamination and propagation delay. So we apply the same terminology here. So this is called as the contamination delay, and this is the propagation delay, TPD. So I have now shown D. D consists of 2 bits, 1:0. Initially, your D1 is going to change, right? So D1 has changed, D0 has not changed till then. And then after a few seconds, your D0 is going to change. So if I were to look at D as an input, initially there is a transition, and then you have one more transition before which it settles. So here TCD is the contamination delay. And TPD is the propagation delay. So now we move on to the sequential circuits. So what are the sequential circuits that you know of? Okay. So latches, then you know about flip-flop. And we'll also take a quick look at what is a register. So now across textbooks, the definitions for latch, flip-flop, and register will vary. We'll stick to the definition used in CMOS VLSI design by Westy and Harris, right? So let us start with a latch. No, actually, let's start with a flip-flop. So we'll draw the timing diagram, identify the delays, and from there, we'll move on to the timing diagram for a latch. Okay? Instead of looking at the transistor level implementation, we will first focus on top level implementation and the timing parameters for a flip-flop. So this has 2 inputs. We are looking at the simplest form of a flip-flop with 2 inputs, data and the clock, and the output Q. So we are considering a positive edge triggered flip-flop. Let's say I have a clock signal as shown here. The data signal is varying like this. Say this is D1. D2. D3. D4 and D5. Can you sketch the output queue? Please sketch. What do you get? So before this clock edge, I don't know what the value of Q is, so I'll leave it as it is. At this clock edge, your output will begin to transition, right? It's possible that you have more than one transition before the output settles. The reason for this transition is different from that of a combinational logic. We'll come to the explanations for this when we deal with transistor level implementation of a flop, right? For now, just assume that corresponding to every transition at the output, it need not be a single transition. You might have more than one transitions before the output settles. What is this value? This is D2. Does D3 come to the output? What is the next output that will come? Directly D4. So you'll have D4 here. So now let me mark the input edges that is causing a transition at the output. So this clock edge has caused this transition. The same clock edge has caused the next transition. What should we call the first delay as? That is from the clock edge to the first point at which the output has started changing. Contamination, but right, it is contamination, but you need some more information, right? Delay, okay. So where is this delay between? Clock to Q. So we call this as clock to Q contamination delay. So this is TCCQ. So here the CQ stands for clock to Q. And this is now clock to Q contamination delay. We also have one more delay parameter from the clock edge to the last point at which the output is still transitioning before it became stable. What should we call this? Clock to Q propagation delay, represented as TPCQ. This is TPCQ. This is clock to Q propagation delay. Okay. So now what you see here is that whenever you have a rising edge in the clock, the input D is sampled and the D is then passed on to the output. So for the flop to sample the data correctly, this has to be set up sometime before the clock edge, right? So if you say sometime before the clock edge, we are engineers, we want specific numbers. So how much time before the clock edge should the data be set up? Right. So this is quantified in terms of the parameter called as setup time. So TSU. Now, the setup time is a property of the flip-flop that is being implemented. So anytime you implement a flop, you would characterize it and find out what is the associated setup time. That is how long before the rising edge of the clock should you set up the data such that that data is sampled correctly to the output. Now, the setup time is sometimes represented as TSU. Sometimes you directly write it as T setup. So this is the setup time for the clock. So sorry, for the flop. Similarly, after the rising edge in the clock, you need to keep that data steady for some more time. And this is quantified using hold time, TH. Again, you represent this as either TH or T hold. This is the hold time. So as long as your data is steady during the setup time and the hold time, you are guaranteed that it will get sampled correctly to the output. Okay, any questions on this? Then let's move on to latches. Again, we'll take the simplest form of a latch. So this has two inputs, data and clock, and it has an output. And latch is level sensitive. It is not sensitive to the edges. It is sensitive to the level of the clock. So let me give you a sample waveform. You can sketch out the output. Please sketch the output. So what I have drawn here is a positive latch. What does this mean? When clock is equal to 1, the latch is transparent. So when clock is equal to 1, the latch is transparent. The input will directly go through to the output. When clock is equal to 0, the latch is opaque. That is, it is holding the previous value. Transparent, it is opaque here. So can you sketch out the waveform? After you have sketched out the waveform, see if you are able to figure out the important delay parameters, the timing parameters for a latch. So you will have the first transition corresponding to the clock edge. And the final value is, this is D2. So I'm not sketching anything here because this region is opaque. It has to hold the previous value. Now, if the value had changed, so before D1, if there was a D0 and that transition happened sometime in the transparent phase, D2 would be appearing here. Sorry, D0 would be appearing here, right? Which is why I'm leaving it blank. So this is D2. Now, corresponding to this, you would have a transition. Then you will have D3. What is the next value that you will see? You will see D4 at what instant? After this clock edge. Everybody got this? Now let's mark out the transitions. So these two transitions are caused by the clock edge. What are the associated delays? So this has to be TCCQ. This is TPCQ. The delay is between clock and the Q, and you have a contamination delay and the propagation delay. What about these two edges? Right. These changes have been caused because of a change in data, not because of a transition in the clock. We write TPCQ here. So the arrows will look like this. And what are the associated delays? What should you call this delay? So this is data to Q contamination delay. So TCDQ. And this is TPDQ. So TCDQ is data to Q contamination delay. TPDQ is data to Q propagation delay. How would you define the setup time for this latch? Yeah, setup time for this latch, how would you define it? It has to be defined with respect to the clock, right? It's a relationship between clock and data. So the setup time has to be defined as some time before a clock edge. Which clock edge should we define the setup time for? Okay, so you're saying that it has to be defined for both the clock edges. When the data is going to change. Okay. So you are saying that, so basically for a positive latch, you are saying that it should be defined with respect to the rising edge of the clock. Is that the... So setup time is a relationship between data and clock. And it is like data has to be set up so much time before the clock edge. So now we have to identify what is the clock edge before which we need to set up the data. Right? So you had an answer? Both edges. So I have got two answers. One is both edges, and you think it's a... Everybody says both the edges. Help me understand why we should be worried about the rising edge. Whether I set up the data here or I set up the data here, it is going to come through to the output. The data changes. So if the data changes here or if the data changes here very close to the clock edge, that is going to come through to the output. Because when clock is 1, the latch is transparent. So what is the sampling edge of the latch now? Falling edge, right? You are sampling the data at the falling edge and holding it. So now if you want the correct data to be held during the opaque phase, then that data has to be set up before the falling edge. Is that statement clear? So the setup time has to be defined with respect to the sampling edge that you are dealing with. For a flop, that sampling edge was the rising edge of the clock in this example, right? Which is why the setup time was defined with respect to the rising edge. Now for this latch, the sampling edge is the falling edge of the clock. Therefore, you define the setup time with respect to the falling edge. So you'll have some setup time here and a hold time again corresponding to the falling edge. This is clear? So if you set up the data sometime here, is that the... Yeah. Then it changes again before the clock. you should be able to define such a time also, right? But that is not the setup time, because if it has changed twice, then the data that you will see this for a short duration at the output, and then it will change again. Is that something that you will require in a design? Is what I'm thinking, because if the data is changing very quickly at the output, the next element will not have enough time to capture it. Whereas holding it is, sampling and holding the data for the next element to capture it is more relevant. But of course, you will be able to define for a given circuit what is the duration for which, what is the duration before the edge that you need to set it up such that it gets to the output. That you will be able to define. But it is not called as a setup time. Okay, so now we know the definition for a flip-flop. We know the definition for a latch. Any guesses on what a register is? Sorry, it stores the data for a given time. So that's what flip-flop also does. More than one bit, right? So a register is basically multiple flops that are tied to the same variable. So for example, in the project given to you, you had to set the variables, you had to set the gain of an op-amp. Right? So I could have two flops. Let's say this is gain A1. How many bits did it have? 3 bits, right? So this will be gain A1 of 1. Gain A1 of 0. All of them are clocked by the same clock. Their D inputs are coming from the SPI related module that you have written. So then this is what we call as a register. Gain A1 is now a register consisting of 3 bits. And it's very common to simply represent it like this. So you'll have a single clock. You have the data coming in, which is 3 bits, say 2:0. And then you have the output with gain A1, 2:0. This is the definition for a register. So let me go back to the latch again. Right? And we said that this was a positive latch. If I had to describe its behavior between the inputs and the outputs, let's say in English, how would I write it? Yeah. So if clock is 1, then the output is D. Right? So I'm not worried about a syntax because this is not even Verilog. I'm simply describing this in English. Else if clock is equal to 0, then the output is Q. So how do you implement this? How do you implement this? If I've given you this description, what is the first circuit that comes to your mind? Mux, right? So let us implement this with a mux. So this has 2 inputs. Select signal is the clock. When clock is equal to 1, the clock is equal to 1, the output has to be same as the input. When clock is equal to 0, you have to connect it like this. We have implemented a positive latch. Can you quickly implement this using transmission gates? You get this implementation. Okay. So now if I ask you about the delay from data to queue, what comment can you make? Right, but would you be able to estimate the delay, or is some information missing? Right, but what information do you need to be sure about the answer? You need the capacitance at what node? Okay, is that sufficient, or is the drive strength information missing? You also need to know what is driving the D input, right? So in practice, when you put this in circuit, this will be driven by some gate, right? So that information is now missing, which means, so how else what estimate can you make about the current available? Right? So the problem with just calling this, implementing your latch just like this is, of course, you can implement it like this, and then depending on where you use it, you can characterize it, right? But generally, when you design a latch, it is going to be used in multiple places. So if you include the drive strength information also with your design, then it is more usable, right? It just becomes a matter of plug and play. Wherever you want it, you take the full circuit, plug it. It has already been completely characterized with the drive strength of the drive strength that is included with it, right? So what happens is, for all the other implementations, you know what is the input capacitance that you are offering, right? And you know what is the drive strength that is available to you. The only missing information is basically the rise time of the signal at the input, correct? So usually you would make a table, any standard cell you design, any basic module you design, you will have a table for the delay. And the table will have two variable parameters. One is the rise and fall time of the signal being applied. The other is the total load capacitance at the output. Okay, so if you know, if this is a circuit that you have designed, if you know what is the input capacitance your circuit is offering, and if you know what is being driven here, you will know what is the estimate of the rise time and fall time, right? So either you have to give the information about the input capacitance, or you make a table saying that if the rise time here is so much, and if the load that my circuit is seeing is so much, then the delay is this much. So you will have a 2D table with one side being the rise and fall time information, the other side being the capacitance. And now for any value of rise time and the load capacitance combination, you can either pick the value directly from the table, or you can interpolate two values and estimate what is the delay that you expect. So all that calculations you cannot do for this circuit, because you don't know, the drive strength information is now not included with it. So every time you use the circuit, you'll have to see what is driving it, how much load is there, and then estimate the full delay. Right? So if I wanted to include the drive strength information also into the circuit, what change should I make? We add a buffer or an inverter. So where all should I add the buffer and inverter? So we add, let's take an inverter, right? It's easier to deal with. So I add a inverter here. Where else? So I add an inverter at Q. Where else? So let me connect this as. So now when clock is equal to 0, what is the drive strength? So I add another inverter here to solve that problem. Is this okay? Because now when clock is equal to 0, what is driving your output? If this inverter is not here, And let's say clock is equal to 0, which means this is off. And this is the path that is on. Correct? So you are driving the output node like this. Correct? So to find out what the drive strength is, I simply include that information by including an inverter here. So I'll come to that, right? But the drive strength including part, is it clear? It's either an inverter or a buffer, right? I include that here. So now the problem is, what is the direction of the feedback in this path? So find the direction of the feedback. I break the loop here. If I increase the voltage at this node, the voltage at this node also increases. What happens to the voltage at this node? This will also increase. So if clock is equal to 0, you have a positive feedback here, right? Now I have to make sure that the feedback remains positive even when clock is equal to 0. This is one part. The other part is, I gave data here, I'm getting data bar here, if the top path was on. So to do this, let's say I included inverters in both the paths. Okay, ask your questions. So I started with transmission gates, right? There is no CMOS. So you're saying use and not, etc., and then implement the mux? It is possible to implement using other combinational logic, but we know that mux is the simplest implementation for a mux is using the transmission gates. So we simply used that as a starting point, right? Given that we have used that as a starting point, and I'm simply inserting inverters, right? So I have gotten a configuration here. Does the circuit have a problem? Okay. Right. So this circuit has a problem, right? And the problem is this output node is now being driven by two inverters, right? Earlier, it was being driven by two transmission gates, where only one transmission gate was on at a time, right? Because of which there was no conflict. So the earlier scenario, so let me simply show the transmission gate as a switch now. So you had clock here and clock bar here. So earlier you had either clock path on or clock bar path on. So there was no conflict. You had a single driver driving this node. Right now, because I have added two inverters like this, it is possible that you can have a conflict. Even when clock is equal to 0, the capacitor here is going to store some value. So the capacitor here, both these capacitors are going to store some value. And let's say the D is equal to 1, which means you would expect this node to be equal to 1. But at the same time, if this node had the value 1 volt, logic 1, this path is going to try and drive 0 to this node. So you are trying to drive the same node with 1 and 0. And if both these inverters were identical, very high chances that you will be around the midpoint voltage. Now, how can I correct it? So clearly, the shorting has to happen here at the output of the multiplexers. So then I don't need to have two inverters. The circuit can simply be this. Is this okay? Now let me redraw this circuit. In a manner that you probably have seen before. So from now on, instead of drawing the transmission gate like this, I will simply replace it with a symbol of a switch. So if I show something like this, it means that this is a transmission gate that is turning on when clock is equal to 1. So let us redraw this. You have D. Then you have this inverter, followed by a switch, which is operating at the clock. What do you have then? One more inverter. This is your output. The output is tapped, goes to the input of another inverter. Then you have another switch, which turns on at clock bar. And then this is shorted. Have you seen the circuit before? So this is a latch with an inverter included in this. So quickly tell me, is the circuit on your left a static circuit or a dynamic circuit? So both are equivalent. Is it static circuit or dynamic circuit? How do you determine whether a circuit is static or dynamic? Whether clock is high or not? But is that the only condition? So we are talking about whether the storage is static or dynamic. So whether we are relying on the whether there is any node that is floating at any point of time, and we rely on that floating node holding its charge. Right? If it is static, then all nodes are at all times connected to either VDD or ground. If it's dynamic, you can have floating nodes, and the circuit functioning correctly relies on that floating node holding its charge correctly. This is static. Why? I can't hear you. Correct. So let's quickly check this, right? So I will mark all the nodes. Node 1. This is another node. You have one node here. This is another node. And this is the final node. So D, of course, is being driven by some driver. This is being driven by an inverter. Therefore, it is never floating. This node is either driven by this path or by this path. Right? So this is never floating. This is again driven by an inverter. This is also driven by an inverter. So this is now a static implementation of a latch. I also want to take a quick look at these two back-to-back connected inverters. Let this node be Vn. This is V0, I1, and I2. I want to plot the VTC for both I1 and I2, but on the same curve. The x-axis is V0, sorry, y-axis is V0, x-axis is Vn. Can you plot the VTC for both I1 and I2 on the same graph? How does the curve for I2 look like? Should look like this. So now the stable points for this circuit is obtained at the points where the two curves are intersecting, right? Which is at So this is 0.1. Let's call this as 0.2. And finally, you have a 0.3. So when Vn for case 1, if Vn, what is the value of Vn for case 1? Yeah. Vn is equal to 0. And what is the output? V out is at VDD. For case 2, what is the value of Vn? Vn is at VDD. And the blue curve's value is 0. This is okay. Case 3, what are the values? Right. Both of them are at the midpoint voltage. So clearly, case 1 and case 2 are stable, right? If both of these are inverters, if input is 0, the output is VDD and vice versa. So case 1 and case 2 are stable. What is special about case 3? It is stable as long as there are no other disturbances, right? If you slightly change one of the voltages, let's say it has settled at Vm, no other disturbances, it will remain in that state for a very long time. If you slightly change one of the voltages, it is going to proceed towards either state 1 or state 2. For example, let's say that this was the original midpoint voltage and I shift it slightly to this new value. So corresponding to that, you are now at this location in the curve. The input has increased and the output has slightly decreased. Correct? So now if the output of I2 has decreased, this is the input for I1, which means now you are here on the curve, which means now the output of I2 has gone to VDD. So from the midpoint voltage, I slightly increased my Vn and it has gone all the way to VDD. If I had slightly decreased Vn, this would go all the way to 0, right? So this way, this node is metastable. Now, if you implement this on a circuit, on a practical hardware, you will eventually come out of metastability. You will either go to 0 or VDD because there is so much noise involved in the circuit. You have thermal noise, flicker noise, power supply will have a noise. Signals changing around you is going to couple due to capacitive coupling, or it can couple to the power supply or ground. So you have noise. So this is definitely going to either come to 0 or VDD. Now, how long it takes to come out of the metastability and to what value it is going to settle to, both of these are now a function of the noise, right? And you don't have much control over it. Correct. Now, if the slope, so noise is a continuous thing happening, right? So if you had a small noise in positive direction and another, right? So you can be in the metastable region for quite some time. And how long it remains there is also not really under our control. So metastability, in digital circuits, we don't want this because it is indeterminate region. It's neither logic 0 nor logic 1. So entering into metastability is also a problem because we don't know for how long it is going to be in metastable regions. So this is something that we want to try and avoid in our circuit, right? And because this is now in positive feedback, and if you are very careful in the way how you are setting up this circuit, if you make sure this logic is nicely settled, then you don't have to worry about metastability because you are starting off with either region 1 or region 2. Okay. So any questions on this? So now let us talk about what happens if we start cascading multiple latches. So I'm going to use the simplest example of latch as a mux, and I'm going to cascade 2 latches. You can tell me what is the functionality. Is this a positive latch or a negative latch? Why is it positive? It's a negative latch. When clock is 0, your data is going to come to the output. What about the second latch? So this is a positive latch. Tell me after you have drawn the waveforms. So I will call this node as QM, the intermediate node, and this is Q. Can you plot QM and Q for this configuration? So latch 1 is a negative latch, which means it's going to be opaque during these phases and transparent when clock is 0. Latch 2 is transparent when clock is 1 and opaque when clock is 0. So I can simply look at this and then sketch QM. QM is the path from data to, it is the output of latch 1. So let's say that, okay, here the value settles to D2. Then it changes to D3 here. Changes to D4. And it changes to D5 corresponding to the clock edge. Now, of course, you can show the in-between transitions also to account for the propagation and the contamination delay. For Q, QM is the input. We have to simply look at the state of latch 2. So latch 2 is transparent here. So at this clock edge, you have a transition. This is D2. At the falling edge, latch 2 has become opaque. Therefore, any change at the input doesn't come through to the output. And you have the next transition here, D4, and so on. Everybody got this? Right? What does the circuit implement? This is a flip-flop. This is a positive edge-triggered flop. And this implementation style, where you have two latches in cascade, is called as the master-slave configuration. So the first latch is called as the master latch. And the latch that follows is your slave latch. And can you see the beauty of this? You have taken two individual components that are sensitive to the levels. And then you have put them in cascade to obtain a component which is sensitive to an edge. Now this is possible because in this particular case, you had a negative latch in the front. So when that negative latch is transparent, the slave latch, which is sensitive to the positive edge of the clock, is opaque. So any change happening at the input doesn't go through to the output. It simply reaches till the midpoint, QM. And then the master latch becomes opaque. So changes at the output does not affect QM. QM is constant. And the slave latch becomes transparent so that the QM propagates to Q. So during first half of the clock cycle, you have QM. So first half of the clock cycle here, QM is constant, right? Therefore, Q doesn't change. During the second half of the clock cycle, latch 2 is off. So any changes in QM doesn't affect Q. And the transitions now nicely happen only at the positive edges of the clock. Correct. If you use two positive latches and then instead of clock and clock bar, instead of giving both as clock, you can use clock and clock bar. That is also another possibility. So I'll give you a quick homework. One is implement negative edge triggered flip-flop. Also analyze the timing diagram. So I'll make his suggestion as another question. Implement a positive edge triggered flop using two positive latches. Oh. So now coming back to this diagram we have drawn here, what is our sampling clock edge now? Positive edge, right? So now let's say I want to find out what is the setup time for this flop. And you are given the setup time for the individual latches. You are given the whole time, TPCQ, TCCQ, everything for the individual latches. Can you tell me what would be the setup time for this flop in terms of these parameters? So the question is, how long before the rising edges of the clock should the data be set up such that it is appearing at the output correctly? And you know this information for the individual latches. Why do you say it should be setup time of L2? So what is the sampling edge for L2? Negative edge, right? So that itself tells you that something is off, right? L1 is the bottleneck. Why do you say that? Correct, right? So L1 being the bottleneck is clear to everyone, right? If L1 has sampled the data correctly, then so L1 has sampled the data correctly before the rising edge of the clock, before it turns opaque. Then it means that QM has been set up correctly and it will definitely appear at the output because in the after the clock has risen, L2 is transparent, right? So L1 is the bottleneck. So if L1 setup time criteria is met, the flop's setup time criteria is also met. Is that clear? So the answer is this should be equal to TSU of L1. Any questions on this? If the setup time of L1 has been met, it means that before L1 turns opaque, the data has been set up correctly at QM. I mean, it is guaranteed that the data is going to get set up at QM during the phase when L1 is opaque. L1 is going to hold that data during that complete phase, right? And if QM has been set up correctly, Q is going to get set up correctly automatically. Therefore, the setup time constraint of L1 has to be met. So TSU of FF will be equal to TSU of L1. So also think about what should be the TPCQ, the propagation delay, clock to cube propagation delay of the flip-flop. Again, you are given all the parameters associated with the individual latches. So in analyzing the clock to Q delay, please assume that the data has changed much before the setup time of the flop. Why do you say it should be the sum of both? Both the latches to. Is that statement correct? So the data has been set up at D much before the setup time of latch 1. Right. So what should be the TPCQ of the flop? This should be equal to TPCQ of it. Is this clear? Ask your turn. Okay. So if the data has been set up much before the setup time of D, that means the data has already reached QM. So with that assumption, then it is TPCQ of the L2. Okay. So the rising edge has occurred in the clock. From the rising edge of the clock, how much time does QM take to appear at Q? TPDQ will also be the TPDQ will also be the same if the setup time constraint is well met with sufficient positives. Yeah. So you can think about all the other parameters for the flop, such as TCCQ, TPDQ, TCDQ. Is there a TCDQ and TPDQ for the flop? For a latch, it is more relevant. So we define these parameters for the flop for during the characterization purposes, but otherwise it's not very relevant. Clock to queue is more relevant during system design than the data to queue delay, because you expect the data to queue delay to happen at the you expect transitions to happen at the clock edge than at the data edge. But during characterization of a flop, you will look at these parameters also, data to queue delay. And I will explain that when we are trying to characterize the setup time for the flop. So that we will explain a little later. So hold time for this circuit in general, right? So in general, the idea is you have a clock edge, right? So your data, let's say, is changing before and after the clock edge. But the data that you want to hold, let's say, is this, some D1, right? You want D1 to appear at the output queue, which means D1 has to be set up sometime before the clock edge. That is what we define as TSU. And the D1 should remain stable for some time after the clock edge. This is called as TH. Now, if this transition happens much closer, then your data can get corrupted and D2 might appear at the output instead of D2. So around this clock edge, there is a region when your data has to be stable. And this is defined using setup time and the hold time. Could you quickly sketch out the same flip-flop using the configuration we have used here? Instead of a mux, please use switches to represent transmission gates and inverters. Did you get the circuit? Right. So now let me label the individual components. Let's say I1, I2, I3, I4, I5, and I6. Let's say this is TG1, TG2, TG3, and TG4. Okay. Now, roughly, we are going to represent the delay of the component as D, the name of the component as a subscript. So DI1 for the delay of I1, DTG1 for the delay of the first transmission cable. Can you tell me what is the setup time of this flop in terms of these individual delays? Is the question clear? So tell me the thought process first. Setup time. Right. Setup time of the first latch. Now, what is the thought process behind finding the setup time of the first latch? Is reaching till QM sufficient? Why do you say it should reach till QM? It should reach after I1. So till here or here? Till here. Is that correct or is something missing? So D to QM, is that sufficient? D to I4. Why I4? Okay, but if it reaches till QM, then you are sort of guaranteed that it will reach till I4 also, right? So what is the point that you have to be really careful now? It should settle where? It should settle at QM. What do you mean by that? When you say it should settle at QM, it should not enter into metastability, right? So I'll give you a waveform to try out, and that should help you figure out what this is, right? So I'm going to, I'll simply set up the equations, set up the nodes that you have to look for the waveform. Let's say this node is N1. This node I'm going to call as X1. This node is N2. The capacitance at N2 we will call as C2. Capacitance at X1 is, let's say, CX. Okay. Now, the plot that you have to do is, let's say you have a rising edge in clock. And let's say the data is changing just before the clock edge, like very close to the clock edge. You can assume that the data was 0 for all the clock edges before this. Right? So this is the first rising edge in the data that is coming to you. Sketch for N1, N2, and X, and see if you are able to figure out what is the node that you should care about to determine the setup time. Is the nodes clear that you are worried about? So we have gotten multiple answers saying that the data should be stable at N1, should be stable at X1, QM, and after I4. So we have to figure out what is the node that we are really concerned about, right? So please do this sketching, and then we can discuss this in the next class. Thank you.